Welcome back to ECE 220. Today we finish up Lab 0. We won't have to be announcing that anymore. If you're in Section I, make sure you go to Lab today, and you'll need to bring something to take notes with, wear some closed-toed shoes, and bring your CAT card. Homework 3 is also due today, and after that, most of you in Group A need to get started on pre-lab for lab number 1. Your pre-lab needs to be submitted as one PDF file into the Dropbox, and that now is available to you, and make sure you put it in the right location. There's a Dropbox for pre-lab 1 for Group A, which involves all of the sections except Section I. Section E, F, G, and H will submit, and no matter what section you're in, e.g. E, F, G, and H, you will submit on Saturday. It's due on Saturday, even though your lab is on a Tuesday, Wednesday, etc. Homework 4 is due a week from today, and exam number 1 is coming up. That's next week. You need to be thinking about that as you're doing your homework, which is due today. That's homework number 3. That's the last assignment that topic-wise will be covered or dealt with on exam number 1. Today I want to get into supernodes. But before we do that, let's do one more example of node voltage analysis. Supernodes are a part of node voltage analysis, but it's a special case. We'll do one example with multiple source dependent sources before we get into supernodes. And a supernode is, you create that when you have a voltage source between two essential nodes. And that voltage source could be an independent source or a dependent source, voltage source, between those two nodes. Then we'll work through a couple of examples, with the first example hopefully convincing you that a supernode is the way to go in certain situations. Here is an example of node voltage analysis with dependent sources. The goal is to find the power associated with this dependent source, dependent voltage source, that's determined by the current I sub 0. And if you're working all the problems in the back of the book, this one is similar, it's not the same, to problem 21 in chapter 4. What's our first step in the process of performing node voltage analysis? What's step 1? Step 1 finishes with the identification of node voltages, correct? And to get those, we actually need to identify essential nodes. And essential nodes are the connection of 3 or more elements. Here is an essential node. Here is an essential node. Here is an essential node. And there is an essential node. We have 4 essential nodes in this circuit. And consistent with our sort of just immediate choice for a reference node, we would probably select the reference node that is associated with as many elements as possible. In this case, it's the one at the bottom. Let's then make this our reference node.
That why we had to combine it and subtract all the other voltages.
So the question was, yesterday we did an example where the reference wasn't associated with the bottom node, or the one that had all the or more elements connected to it. Is that why we had to subtract node voltages? The purpose of subtracting the node voltages was really just to establish the voltage drop across two nodes. It didn't really have any bearing on how we selected the reference node. So the reason we were subtracting node voltages was just to find the voltage dropped across certain nodes in our circuit or in our network. Let's just go from left to right. If we've now assigned our reference node, let's label this one as V1, V2, and V sub 3. That's now what we needed to do in step 1, was to identify the appropriate node voltages, and we just made those be V1, V2, and V3. Now that we've identified those, we can actually find a formula for I sub 0. We're going to need that if we find the power associated with that dependent source. The dependent source is dependent on I sub 0. We're going to need an expression for that. Let's just go ahead and write that down now that we have these node voltages identified. In terms of how we've defined our node voltages, what's an expression for I sub 0? And that's just Ohm's law, isn't it? It's simply the voltage dropped from left to right. That's going to be consistent to give us a positive expression for Ohm's law relative to how we've defined that current I sub 0. I sub 0 now in step 2, we're trying to write these KCL equations, but before we do that, let's just go ahead and say we'll need I sub 0 because it appears in our dependent sources. We actually have two dependent sources. That one on the left I was kind of neglecting right now because I was focusing on the power of the dependent voltage source, but we also have a dependent current source. I sub 0 is now V2 minus V3 divided by 50. That's an expression for I sub 0. And let's just kind of keep that clearly available to us, because that will allow us to sort of get rid of one of these unknowns that's going to be floating around in our KCL equations in the form of I sub 0. If we now apply KCL at the different nodes, let's just say all currents going out of node 1, 2 I sub 0 is going in, so we have minus 2 I sub 0 going out. Going down, we have V1 over 100. And going to the right, out of node 1, is V1 minus V2 over 25. Those all then sum to 0. We're looking to find write three different KCL equations since we have the 3 node voltages. At node 2, currents going out, we have V2 minus V1 over 25. That's going to the left. V2 over 200, that's going down. And V2 minus V3 over 50, that's going to the right. Those are the 3 currents leaving node 2, and we'll set those equal to 0. That's KCL number 2. Whatever I just said. V2, minus V1 over 25. The down was V2 over 200. And finally, we had V2 minus V sub 3 over 50. And finally, we want to write one more KCL equation relative to node 3. Going to the left, out of node 3 is V3 minus V2 over 50. Going to the right is V3 minus 38.5 divided by 20. And now going down, what's that going to be? Is it 5I0? No, that's a source. And that's going to give us a particular voltage there, and that we can now use to determine the voltage dropped across that resistor, which is V sub 3 minus 5I sub 0 divided by 5. That's KCL number 3. Going left, it was V3 minus V2 over 50, plus going down V3 minus 5I sub 0, that was the dependent voltage source, divided by 5, plus the current going to the right was V sub 3 minus 38.5 over 20, and we'll set that equal to 0. Now we have 4 equations and 4 unknowns. I sub 0 is floating around in there as an unknown. We do have an equation for it, so that star equation is our 4th equation. Let's go ahead and use star and substitute that into 1, 2, and 3 to get rid of at least one of the unknown variables, and then we'll end up with 3 equations and 3 unknowns. If we do that, let me just kind of write some words down. Now we have 4 equations. And 4 unknowns, and the unknowns are I sub 0, V1, V2, and V sub 3. Since we have I sub 0 in terms of V1, V2, and V3, let's eliminate I sub 0 from the final 3 equations. By using equation star. And if we clean everything up by multiplying through by the appropriate values, we'll end up with the following 3 equations. 5V1 minus 8V2 plus 4V sub 3 is equal to 0. Minus 8 V1 plus 13 V sub 2 minus 4 V sub 3 is equal to 0. And finally, the last equation is then minus 4 V sub 2 plus 29 V sub 3 is equal to 192.5. It's time once again for our linear algebra commercial. This is now a linear algebra problem. It's 3 equations and 3 unknowns, and probably most of your calculators can do that. Can they do that? Let me know if they can't or cannot, because the exam, if it can do a 10 by 10, you're good on the exam. Just joking a little bit, but what you could have to do is maybe set one of these up on an exam, or on your homework you might have to find these equations, one or two or all three of these equations, and write those down. But if you now solve that, you'll end up with the following answers. V1 will end up being minus 50 volts. V sub 2 will end up being minus 30 volts. And V sub 3 is equal to 2.5 volts. What magic happened from blue to black? The magic that happened is the first step was I replaced I sub 0 with this starred representation. Everywhere I found an I sub 0, I replaced it with V2 minus V3 over 50. Then I just cleared the fractions and combined the variables, and that then simplifies. So there's a couple of steps involved to get from blue to black. Once you have this, now you have three equations and three unknowns, which allows you then to solve using a calculator to obtain those node voltages. And once we now have those node voltages, we can solve for whatever we need in that particular circuit. And what were we question? How did I determine where I placed I sub 0? That was a given. I sub 0 is a dependent current that is given to you, so that was a part of the problem. So I didn't have the choice in I sub 0. The question was, how did I decide to put I sub 0 where it was at? And I didn't. That's just what you would be given on a problem. And then these two dependent sources depend on that current I sub 0. So now you're given that information. You then had to find the node voltages and analyze the circuit based on that given information. So you're given I sub 0 and how it is related to your dependent sources, the dependent current source and the dependent voltage source. Now what we want to do is figure out the power associated with that dependent voltage source that's 5 I sub 0 in voltage. How do we find that power? How do we find the power associated with any element? You're texting, right? So now you have the passive sign convention. PSC, you need what? A voltage and a current. Their product gives you the power associated with any element. We have a formula for I sub 0. We have the voltage then of that dependent source. We have 5 I sub 0 in terms of V2 and V3. We need the current. We could, just to give us something to label it, we could say, well, let's just say that we have that as our current associated with that dependent voltage source. We're just, this one now I created. This I sub x, I simply said this is going to help me. Let me just put it here. If I now have this information in front of me, can you at least find an expression for the power associated with that dependent voltage source? P sub 5 I sub 0. Isn't that the voltage times the current, and what's the sign on that expression? Positive or negative, based on the passive sign convention? Positive, because the current's hitting the positive terminal that we have labeled before it goes through the element. And what does that mean? That means whatever that product yields is the amount of power absorbed by that circuit element. If the result ends up being negative, absorbed, then you really have that magnitude of power supplied to the rest of the circuit. Or delivered, or I think the book even says developed. What did we just say? We now have an ability, or formulas, to find this expression. Wow, I'm really having issues today. P sub 5 sub I sub 0 is the voltage times the current, and with the passive sign convention, that's a positive. Questions on where that came from? Pardon? Yes, the voltage of that dependent source is specified as 5I sub 0. It's a dependent source. That's our voltage. The current is I sub x. We now need I sub 0, but that was V sub 2 minus V sub 3 over 50. And that ends up being minus 0.65 amps. And I sub x is V sub 3 minus the voltage associated with that dependent source divided by 5. And if you plug in the numbers that we have now determined, that ends up being 1.15 amps. Or P sub 5 I sub 0 is now 5 I sub 0 I sub x, which is now minus 5 times 0.65 times 1.15, and all of that multiplied out gives us minus 3.7375 watts absorbed. Or we could also state that as 3.7375 watts delivered, supplied, developed by that dependent voltage source. So it's 3.7375 delivered, or supplied, or developed. Again, those are meaning the same thing, those words. That's node voltage analysis, fairly standard. It's just now with dependent sources. Let's kick it up a notch and say, what if somebody gives us this scenario in a circuit? This is now extracted from some more complex network, and we have identified node A and node B with node voltage V sub A and node voltage V sub B and a current I. And what do we know about I going through that voltage source? What can we say about I, or what is I out of A? it's going to be whatever it needs to be to give you, if that voltage source has a value of V, that's an independent voltage source, it's going to give you V, it's going to give you whatever I needs to be to maintain V across nodes A and B. Meaning, what is I out of A? It's really unknown. And what is I into B? It's the same I. That's also unknown. Those two are really going to be, or I is going to be determined by the voltage source and the conditions surrounding it. But that voltage source, if it's ideal, is going to give you whatever I needs to be in order to satisfy KCL at node A and node B to maintain V across the terminals of that voltage source. I is going to be kind of a challenge then when we're solving circuit problems. And to avoid it, we're going to just enclose that whole mess into a supernode. That it's no longer just a node, it's a supernode. It's now enclosing. This is that enclosed boundary that we were talking about yesterday. Now we can apply KCL relative to this supernode. We now find all the branches that are leaving that circuit node, and we sum the currents algebraically relative to that supernode. Let's see this in action. Here's a particular circuit, and in this case, let's say it's begging to be evaluated or analyzed using node voltage analysis. And one of the reasons is because we have current sources that are supplying the nodes associated with this circuit. How many essential nodes do we have? Or where are they in this circuit? I heard a 3. Did anyone else hear a 3? There's 1. There's 2. And these are bigger circles if you want. I could make the first one go quite a bit further to the left and encircle that entire wire coming up from the current source I1. Similarly with the second one, and then we have this essential node. Yes, we do have 3 essential nodes. Let's go ahead and make this our reference. And when that's the reference, then that's at 0 volts. In the lab, that's where we would connect our negative lead if we hook this up or we're evaluating this or measuring this with the digital multimeter. And the red lead or the positive lead we would touch at the node above R1, which let's go ahead and call that V1, and the node above R2 is V sub 2. Now let's just say that we are just glad to be solving this, and we just start solving this using this traditional KVL approach or node voltage analysis approach, and we start writing KCL equations at node number 1. What's KCL at 1? I1 is coming in, so minus I1 is going out. Let's just write it as minus I sub 1. Going down, V1 over R1. and going to the right. Ooh. What do we do here? Do we drop back and punt? Suppose we just label that and say, oh, that's I coming out of there for now. Let's just do that bookkeeping and say, I don't know what it is, but V sub S is going to supply it. Let's just call that I. And that's now equal to 0. What if we applied KCL at the second node? We have minus I coming in from the left. I'm sorry, minus I going out to the left. I was coming in from the right. So minus, is it okay that this is now minus I? What's going down through R2? That's V2 over R2. And then we have minus I sub 2.
If we're using the big I sub 1 on the left-hand side of V1, coming in on the right of V2, wouldn't it just be minus I2?
So
we have minus little I there, referencing coming around.
On the right, at node 2, we have minus I plus V2 over R2 minus I2 equal to 0. That's what we would end up with. Now we have two equations in three unknowns. That I is giving us issues. But look what happens if we simply add or combine these two equations. What if we now add these? What results? Do you see that the I and the minus I are gone? They cancel each other out. If we add these two, we have minus I1 plus V1 over R1 plus V sub 2 over R sub 2 minus I sub 2 equals 0. But that is the same as what we would have obtained if we would have applied KCL to this supernode. What if we write KCL at this supernode? We have minus I1 coming in. We maintain the node voltage labels. To the left going down, we have V1 over R1. To the right going down, we have V2 over R2. And to the right going out, we have minus I sub 2. That's exactly what we ended up with without having to write two equations. We just wrote one, and this is now KCL at the supernode. By writing or by introducing a supernode, we eliminated quite a few steps and found the formula that we really can use in one step. We essentially neglected or put underneath the rug this information that's happening inside the supernode. We don't know what's going to happen. Let's just forget it for now and keep track of what we do have a handle on, which are these node voltages and these current sources. Bottom line, could you see how we would do that immediately? We identify our node voltages, and then we say, wait a minute, I have a voltage supply in between two essential nodes, or two of my node voltages. I'm going to enclose that whole thing as a supernode and just write the one equation associated with KCL at that supernode. If we're paying attention, though, what do we have here? We have one equation. How many unknowns? I sub 1 and I sub 2 are given, but we still do not know V1 and V2. We have two unknowns in one equation. We need another equation. Looking at this circuit, do you see how to find another independent equation? Well, we've kind of exhausted all of our KCL potential, but what if we were to now write a KVL that would relate V1, V2, and this voltage source that's given that connects those two? What is KVL in blue associated with this circuit? We have V1's negative terminal as the reference, so we're going in minus V1 plus capital V sub S plus V sub 2, and now we're back where we started. That KVL equation is going to save us. That's going to give us a second equation in the two unknowns. So now writing a KVL at, I don't know how to describe this, let's say maybe even at the supernode or involving the supernode, this is now minus V1 plus capital V sub S plus V sub 2 is equal to 0. Or we could put the V sub S on one side and have V sub 1 and V sub 2 on another side. We could write it many different ways. We could say V1 minus V sub 2 is equal to V sub S. Now we have this equation, and we have this equation in terms of V sub 1 and V sub 2, and we can now solve two equations in two unknowns. We didn't specify anything in this problem, so we can't go any further than these formulas for the solution. We didn't specify any of the R's, we didn't specify any of the I's, we didn't specify any of the V sub S, capital V sub S. Suppose you wanted to find little I after you found V1 and V2, could you do it? Can you find I now? If you've solved those two equations in two unknowns. Do you see that you could simply apply KCL at node 1 or node 2 and I is going to be determined? Because we now know I sub 1, we know V sub 1, we know two of the three currents at node 1. The only unknown current is I, and we can solve for it. We can now solve a KCL at node 1 or node 2 to find I. Let's say that we were at node 1 as an illustration. Then we would have minus I1, which is given, plus V1 over R sub 1 plus I is equal to 0. Or now I is equal to capital I sub 1 minus V1 over R1, and we've now solved for little v sub 1, and we now have a formula or an answer for that current I that the voltage source is producing. What did we use to solve this problem? We used some music, didn't we? Thank you. That was right on cue. We rehearsed that, actually. Sure that wasn't picked up, hopefully, on the microphone, but that was actually the supernode making its appearance. So a supernode is what? When do we have a supernode? When you see what, when is that going to turn on the music and say supernode? When are we doing the supernode? When do we do that? When you have a voltage source between two of your node voltages. And that voltage source could be independent or dependent. Let's just write that down as sort of a conclusion. Supernode. That is going to be established, or basically wanting to be used, when two nodes are connected via an independent or a dependent voltage source. That's the supernode. Let's now see how we might use that to analyze this circuit. Has anybody already solved this circuit? I gave you everything you need to solve this circuit. And I gave it to you yesterday. I'm assuming most of you have the answer, yes? What's our first step in this process of analyzing this circuit? And we're assuming everything is in ohms, amps, and volts. I just have numbers there, but let's just assume the units are amps, volts, and ohms. No Ks, no millis, just amps, volts, and ohms for units. Whoa. Hit the wrong button. How do we start? We need essential nodes, don't we? Here's an essential node. Here's an essential node. Here's an essential node. There's an essential node. And here's an essential node. Which one do you guess I'm going to use as the reference?
That would be the same thing as if you extended that to the 100 ohm in the current source. On the very bottom for the reference.
Yes, so that reference is including all of this. Is that what you were asking? Yeah, I just didn't make it quite as long as what I had been before, but all of that blob is now a reference node. Let's just make this our reference node. And let's start labeling node voltages. If we go from left to right, this could be V1. What about this one? Is that V2? Yes, but it's actually determined because it's connecting a voltage source directly to the reference, so we could just call that 60 volts and be done. This is now 60. Whenever we use that node in our equations, we can just not introduce another variable. Let's just call it what it is. Let's call it 60. We don't have to have another unknown. It's given. It's 60. So this is now V sub 2. and this is V sub 3. We've done step 1. Now as you're thinking about how you're going to analyze this circuit, the next thing you, yes? So now the question is, can we write V sub 3 as 175 I sub x? Is that what you're saying? Now, is 175 I sub x, is that dependent source? I have to watch how far out from my laptop I get, but I played it back and it didn't kill anything, so, but I got a good nap in watching. Anyway, where were we? Oh, 175 I sub x. Is its other side directly connected to the reference node? No. So what can we do, though, with that 175 I sub x? It's now a voltage source, and it's connecting two nodes. Let's put it inside a supernode. Meaning the supernode now gets to be even more interesting. We can call this our supernode. Question?
If we have V1 a reference node, would that make 60 a supernode? Like the point would make 60 a supernode, and then that would make V3 175 I sub x?
So now the question was, if we made V1 our reference node, then we would have this 60 voltage supply being in between two essential nodes, and we would make that a supernode. And then V sub 3 you could label as 175 I sub x. Because I sub x is a variable. We're going to have to figure that out. And what is I sub x now? If we're doing this, can we find I sub x? Now that we have all these, and did I say what I wanted to do? I didn't even tell us what the objective was here. Let's say that we want to figure out the power associated with that 60 volt source, that voltage source. That's our objective. Let's say that we want to find the power associated with the 60 volt source. But that's kind of a secondary, that's maybe the ultimate goal, but it's kind of secondary to doing what? Finding V1, V2, and V3. Did I answer your question, I hope, about choosing the reference node? But that makes it, I think, a little bit more challenging, maybe. Now we don't have a dependent source as a reference node. We have a label of specifically 60 as one of our nodes. What's I sub x? In terms of the information on this network, how would we write a formula for I sub x? Well, it's going from reference node to V sub 2, is it not? And if we used our traditional strategy, we go where we're at, which is 0 volts, minus where we're going, V sub 2, divided by the resistance between. That will give us our formula for I sub x. I sub x, if we need it, is now 0 minus V sub 2 over 200. Or this is now minus V sub 2 over 200. And you could have done it the other way. You could have said, well, the current going down is V sub 2 over 200, and I sub x is the negative of that. However you want to do it, or however you see it. But it's Ohm's law. That's I sub x. How do we proceed? Or, what's our formula for the power associated with that 60 volt source? Can we just write down an answer? Now can you write down a formula for the power associated with that 60 volt source? P60 is now 60 times I60, and what's the sign in front of that formula or that expression? Based on the passive sign convention, this will be positive and it will be absorbed. Now it's your chance to go find V1, V2, and V3 and figure out what you find for the power.